This podcast is on interpreting regression output. We will be dissecting the results of a multiple regression analysis, with an eye toward making the correct interpretation of the results, gaining confidence that confronted with similar output, we can make the correct interpretation time after time. I have constructed a hypothetical regression analysis for us to consider. I don't want us to get hung up on variables, so I've kept everything generic for us. The dependent variable is simply y, and the independent variables are simply a, b, and c. The table looks like one that you would see generated by IBM SPSS for statistics, Stata, R, or other statistical software packages. The table is generic, but provides all of the necessary information to make a correct analysis. The far left column, headed by variable, lists our three independent variables, a, b, and c, and the y-intercept, which is often called constant in software output. They mean the same thing. The column headed by lowercase b lists the slope coefficients for the three independent variables, as well as the y-intercept. The column next to it, headed by se, lists the standard errors for the slope coefficients and the y-intercept. Think of standard errors as analogous to margins of error for our estimation of the slope coefficients. Always keep in mind that the parameter estimates for a regression are just that, estimates, and they could be an error removed from the true parameter estimate. The next column, t, is where we find listed the t-statistics for the slope coefficients and the y-intercept. The t-statistics are derived from the formula slope coefficient divided by the standard error of the slope coefficient. The sig column is the statistical significance level of each t-statistic. Below the table, the r-squared is the percentage of the variation in the dependent variable that is explained by the independent variables. The n is the number of valid cases in the analysis. Our first step is to rewrite the results as displayed in the table as an equation. We do this in order to make mathematical sense of the regression analysis. As you may be able to tell, the equation itself is made up of the y-intercept and the slope coefficients, and they are correctly signed, all positive. The figures in parentheses below the y-intercept and slope coefficients are the t-statistics, and we put them in absolute values so that they are always positive, which will make it be easier for us to interpret in the next slides. Below the t-statistics, we have the r-squared from the model, and finally, next to it, the total number of cases. We thus have a neat method of condensing the information in the table and envisioning how the math will work. Let's put this into motion. Our next step is to verbalize the results. I have a simple sentence for us to say. Y is explained by the equation 1 plus 1.5 times A plus 1.75 times B plus 2 times C. I add another sentence to reflect the presence of the y-intercept. The regression line crosses the y-axis when x equals 1. Then, let's try a simple interpretation of the results. We can begin with the unit change interpretation. What happens to the dependent variable when each independent variable changes by a unit. If there's a unit increase in each independent variable, then we solve this equation by y equals 1 plus 1.5 times 1 plus 1.75 times 1 plus 2 times 1. Thus, y equals 1 plus 1.5 plus 1.75 plus 2, so y equals 5.25 if each independent variable increases by 1 unit. We can break down the results even further by examining the slope coefficients, leaving the y-intercept aside for the moment. Remember, the general language is that when the independent variable changes by 1 unit, the dependent variable changes by the amount of the slope coefficient. Also, please remember that the signs of the slope coefficients are important to keep track of. If the slope coefficient is negative, that a 1-unit increase in the independent variable results in a decrease of the dependent variable by the slope coefficient value. Thus, in order, for each independent variable, we proceed as follows. As A increases by 1 unit, Y increases by 1.5. As B increases by 1 unit, Y increases by 1.75. As C increases by 1 unit, Y increases by 2. Now it is time for us to assess statistical significance. This is important because if the estimated slope coefficients are not statistically significant, then those coefficients are effectively no different from being zero, or having no influence on the rise and fall of the dependent variable. How do we know if the slope coefficient is statistically significant? We will use the rule of 2 to help us make the correct decision. If the absolute value of the t-statistic is greater than or equal to 2, then we reject the null hypothesis that the independent variable slope coefficient is no different from 0. We move on to making the correct interpretation of the sig statistic. We need to remember that our decisions, in a sense, run in opposite directions than with the t-statistic. The higher the value for sig, the greater the statistical insignificance. And the lower the value for sig, the greater the statistical significance. We use the rule of 2 for the sig. If the sig level is less than or equal to 0.05, we reject the null hypothesis that's statistically insignificant in explaining variation in the dependent variable. The independent variable slope coefficient is thus very different from 0. And if the sig level is greater than 0.05, we accept the null hypothesis. The independent variable is statistically insignificant in explaining variation in the dependent variable, and the slope coefficient is no different, statistically speaking, from 0. We will now make a correct interpretation of the statistical significance of the independent variable A. The t-statistic for A is 3.0. Let's recall that the t-statistic is derived from dividing the slope coefficient by its standard error. We want to know the absolute value of the t-statistic so that we can apply our rule of 2. Since positive numbers always remain positive in absolute terms, we simply interpret our t-statistic as 3.0. Since 3.0 is greater than 2.0, we reject the null hypothesis and accept the alternative hypothesis, concluding that the slope coefficient is not 0. Instead, the slope coefficient is most likely to be 1.5. We further confirm the statistical significance of the A variable by examining the sig statistic. The sig is 0.01, less than 0.05, meaning that we reject the null hypothesis and the slope coefficient significantly explains variation. Next, we move on to a correct interpretation of the statistical significance of the independent variable B. The t-statistic for B is 1.75. Again, the t-statistic is derived from dividing the slope coefficient by its standard error. We do want to know the absolute value of the t-statistic so that we can apply our rule of 2. And since positive numbers always remain positive in absolute terms, we simply interpret our t-statistic as 1.75. Since 1.75 is less than 2, we accept the null hypothesis and reject the alternative hypothesis, concluding that the slope coefficient is statistically no different from 0, and the true slope coefficient could well be 0. We further confirm the statistical insignificance of the B variable by examining the sig statistic. The sig is 0.08, greater than 0.05, meaning again that we accept the null hypothesis and the slope coefficient significantly does not explain variation in the dependent variable. Now it is time to make a correct interpretation of the statistical significance of the independent variable C. The t-statistic for C is 4.0 and comes from the slope coefficient of 2 divided by the standard error of 0.5. The absolute value of 4.0 is 4.0. Since 4.0 is greater than 2.0, we reject the null hypothesis and accept the alternative hypothesis, concluding that the slope coefficient is not 0. Instead, the slope coefficient is most likely to be 2.0. We further confirm the statistical significance of the C variable by examining the sig statistic. The sig is 0.01, less than 0.05, meaning that we reject the null hypothesis, and the slope coefficient for C significantly explains variation in Y. Finally, we correctly interpret the statistical significance of the y-intercept constant. The t-statistic for constant is 4.0, which comes from the y-intercept of 1 divided by 0.25. The absolute value of 4.0 is 4.0. Since 4.0 is greater than 2.0, we reject the null hypothesis and accept the alternative hypothesis, concluding that the y-intercept is not 0. Instead, the y-intercept is most likely to be 1. Unlike the slope coefficients associated with the independent variables a, b, and c, the constant does not explain variation in the dependent variable, but rather is where the mythical regression line crosses the y-axis, and is instrumental in deriving the full effect of the independent variables on the dependent variable by solving the regression equation. We further confirm that the statistical significance of the constant by examining the sig statistic. The sig is 0.01, less than 0.05, meaning that we reject the null hypothesis, and the y-intercept is most likely to be 1.0. We conclude our exercise with the interpretation of r-squared. Remember that it expresses the percentage of variation explained in the dependent variable by all of the independent variables. The percentage of variation that is not explained by the independent variables is found by the equation 1 minus r-squared. As you can see, there are rules of thumb for the strength of the models based on r-squared. An r-squared of greater than or equal to 0.50, or 50% of the variation in the dependent variable explained by the independent variables, is a strong model, while an r-squared between 0.2 and 0.5 is a moderate model, and an r-squared below 0.2 is weak. For our model, the r-squared is 0.42, which puts the model firmly in the moderate camp. There's room for improvement in the model in terms of explaining variation, and the b independent variable is not statistically significant, which suggests we should perhaps look for more independent variables to boost the r-squared statistic, so long as those independent variables are theoretically relevant in explaining variation in the dependent variable. Thank you for watching and listening, and take a Zen moment for yourselves after all of that interpretation.